Let me quickly start now. So, like I said, that we're going to learn about TensorFlow and Keras. So, TensorFlow, I've already told that it's like an open source software library which any one of us can use using pip install. And we can use it to solve our projects which are relevant to machine learning or artificial intelligence. There's another library which basically was independent called Keras, but now it's a part of TensorFlow library itself. Keras library is basically specifically for deep learning tasks. So whenever in TensorFlow you're trying to do any deep learning task, you will find the pre-built functions inside Keras. Okay. Let's look at it practically. So what I'll do is instead of complicating and trying to solve the project directly, we'll try to process the text and try to learn the steps that are involved in processing the text first, and then we will move on to the real project. Okay, that will literally just simplify and we would have, modularized everything. Great, let's start. So like we are talking about textual sentences, right? Our ultimate project is going to be that you have a text sentence, and based on that, you're trying to predict whether or not a text sentence is sarcastic or not, right? So before reaching that, let's see first ki how should we give text as an input to the machine learning model to finally learn, right? So I have just taken a few sample sentences here. Now, very important to know, I'm sure majority of you guys know, but uh, machine or like basically any kind of machine, it cannot understand anything apart from numbers, not images, not voice, not text, words, alphabets, nothing at all, right? It can only and only understand numbers. Okay, is it clear to you guys? So in any problem that, any project you're trying to do, your first step would be how to convert this into numerical. So first we'll try to learn that how will TensorFlow help us? Again, our main focus is on TensorFlow. There might be multiple ways of doing these same things, but since our focus is on TensorFlow, we'll try to see how using TensorFlow we can convert the text to numericals. So these are our simple sentences. Now in this TensorFlow Keras pre-processing text, we are going to use the pre-built class tokenizer. Why? To basically convert text to number. So let's try to create a tokenizer object of this tokenizer class, which TensorFlow has already given to us, right? I'll talk about these arguments later, number of words equal to 100. Let's try to ignore that for now. Just see that we have, imported tokenizer class and we are trying to create a project of that type. Now, when in tokenizer, I call the function fit on text, like right, that for a class, when you define a class, you can also define functions in that, right? So these functions I have not created. I've just imported it from the TensorFlow, and now I can literally just use it. That is the whole point of having libraries. So I created a tokenizer object. I called the pre-built function tokenizer.fitOnText sentences. And what it will do in return is this tokenizer, it will take each and every word of my sentences and assign a number to it, right? So this is the output of tokenizer. If you call tokenizer on any list of sentences, textual sentences, what is it going to do? It is going to assign a number to each and every word that you have. So then when you have to convert a sentence to numerical, it is going to look somewhat like this, that whatever tokenizer has assigned IDs to, you literally just replace it with the corresponding ID and you have the numerical version of that text sentence. So for example, my is 2, dog is 3, loves is 7, and cat is 5. Now this is something which tokenizer is going to do for you, and you don't have to basically implement the logic. But just for the sake of understanding, let's try to see how tokenizer is exactly assigning these numbers to these words. Okay. So what it does, what is its main goal? Its main goal is to assign some number to each and every word. So what are all the words that are present here in sentences? I love my dog. And before you guys ask me, it ignores capitalization and it ignores any special characters. Okay. Just separated by space, whatever words are there, it will list them down. Then I is already done. Love my cat. Cat is a new word. You love my dog. You is a new word. Dog loves cat. So we have, this is our vocabulary. This is the list of words that we are supposed to assign a number to. Okay. Now, how is tokenizer exactly assigning these numbers to them? Based on the priority order frequency of word first. That means word that is occurring more number of times in the sentences will be given the, first priority. Then words which are not occurring that many times, right? And let's say if there are two words or more words which have the same frequency, that is, they're occurring for the same number of times, then the second priority will come into picture, that is sequence. That means which word is occurring first in the list of sentences, right? So let's quickly see by, seeing it practically. Again, you don't need to understand this, but just for the sake of it, that what is happening in the backend, I'm telling you this. So firstly, let's try to see the frequency of each and every word. So I occurs 2 times, love occurs 3 times, my occurs 3 times, dog occurs 3 times, cat occurs 2 times, you 1, loves 1. Right? Now, which is the highest frequency, and the numbers that we are supposed to assign will start from 1. Right? So how many words are there? 1, 2, 3, 4, 5, 6, 7. Right? So these are the numbers that we are supposed to assign to each of these words. Now, first for ID1, ID1 should be assigned to which word? The highest frequency word. Now, love my dog. 3 words are there who have the highest frequency, right? So what we'll do in this case, we'll move on to the second priority, that is sequences. Which word is occurring first? Love is occurring first, right? So ID1 will be given to this. Then next priority will be my and dog. Again, my and dog, both of them have frequency equivalent to 3. So again, we'll move on to the next priority order, that is sequences. So my is occurring first, dog is occurring later. Now for word ID 4, the next priority of frequency will be 2, right? So cat and I, there are 2 words which have the frequency 2. So obviously the first priority will be given to the one that is occurring first. So I is occurring first in the sentence. So ID 4 is given to this, and cat is occurring later. So ID 5, you, then we have next priority will be frequency 1. Again, you and loves, there are 2 words which have frequency 1. So we'll prioritize the sequence order. So this will be 6, this will be 7. Now let's check whether, whatever I have explained is correct or not. So love has been assigned ID 1 automatically using the tokenizer. And we see that yes, even by our understanding, love is ID 1, my is ID 2, dog is ID 3, I is ID 4, correct. Then cat is ID 5, you is ID 6, loves is ID 7. Okay, I hope you understood this. So this is how tokenizer basically assigns numbers to each and every word. And now when we have the tokenizer already given IDs, numeric ID to each and every word, we can take the sentence, and for each and every word in the sentence, we can assign the corresponding ID. So for example, here my is 2, dog is 3, gloves is 7, cat is 5, right? This is how we have converted it into a numerical sentence. Now, let's move on to this next sentence. My hamster loves dog. Now we have my, yes. So ID2 will be assigned to, comma, hamster. Do you see any hamster in our tokenizer dictionary? No. So that means it does not consider hamster as a valid word here. Though hamster is a valid word, but since our tokenizer dictionary did not have that as a key, it has been ignored. Next is loves. So loves is 7, dog is 3. Right? So 2, 7, 3. Now there is something really, really wrong about, this representation, because hamster, though it's an actual word, we are giving it literally, like we are not even giving any sort of representation to the word hamster. And there are always going to be words that will not be there in your training data set, correct? There are new words being introduced every now and then. And so there is no possibility that you are able to have all the words that are supposed to occur in the test sentence in the training data, right? So we need to find a solution for this, that though we won't know the meaning of this word since it was not in our training data, but at least there should be some representation here so that we know that, yeah, it was a four-length sentence and not literally just ignore it, right? So here's the solution for it. In this tokenizer object that we introduced earlier, we'll call the tokenizer object and we'll use the arguments. Again, ignore this for now, number of words. We'll introduce an argument called OOV token. Okay. What does OOV stands for? Out of vocabulary. OOV means out of vocabulary. So we have introduced in tokenizer that you don't need to just rely on the training sentences, but you need to assign some ID to the out of vocabulary token, right? So we go through the same thing that we went through earlier, just with this change. And this is the tokenizer dictionary that resulted here. Now, what will happen here? Whenever I say OOV token in tokenizer dictionary, it will assign ID1 to OOV token, right? Once OV1 has been assigned, then from 2 onwards, IDs will be assigned to the rest of the words that are there in the training sentence, right? So if love was 1 earlier, it will become 2. My was 2, it has become 3. So everything has shifted by 1 basically because we have given ID 1 to out of vocabulary. Okay, so this is now our updated tokenizer dictionary, which also has a representation for words which are not there in the training data. Okay. So now if I try to kind of have a sentence that has words which are not which were not there in the initial set of sentences, then uh, this is how the representation is going to be like. My is ID3. So we have assigned ID3. Giraffe, we can see that in the tokenizer dictionary, we don't see the word giraffe. Now, what will happen if the word is not there in the tokenizer dictionary? It will instantly be or automatically be associated with the out of vocabulary token. Because that was the whole concept of introducing that, right? We need to give some kind of representation to this word, right? Rather than ignoring it. So giraffe becomes out of vocabulary. So we give the ID1. Then loves we have out here 8, right? So we have written 8. Dog is 4. XYZ, again a word that is not there in the tokenizer dictionary. So it gets associated to OV and we get the ID1. Okay. OV is 1 by default or we can decide its value. There's a reason that we have given it out of vocabulary token as ID1. That is because we can't give ID 0 and we can't give ID, let's say 9, because you will never know how many words are lying there in the training sentences, right? Let's say if I assign out of vocabulary ID, let's say 100 by default, that every time give out of vocabulary ID 100. But then we have no scope of, keeping a track of how many maximum words are going to be there in the initial sentences. So safe side, we always put OV as ID1. Now, some of you might be thinking that why not 0 and let everything be as it is, as it was in this tokenizer dictionary, that is love 1, my 2, and just add OOV as 0 here. So there's an explanation for that, which we'll, know in this current project itself, but later on. But I hope you got key, why do we not choose any other number other than 1? For not giving OOV token ID 0, we'll definitely address that in this notebook itself. Okay. Can you give a short summary of what is stored? Sure. So basically what we have done yet is that we are just trying to convert textual sentences to numericals, because machines cannot understand words, images, or any other kind of media. It can only and only understand numbers, right? So we need to find a way to kind of convert it into numerical. So since this masterclass is about TensorFlow, we have used TensorFlow Keras to kind of use its pre-built classes and functions to convert sentences into numericals, right? And we use tokenizer here, and tokenizer basically assigns a numerical ID to each and every word that is there in its training data, right? And obviously, there are going to be words which will be left out of the training data. Hence, we introduce the OV token, which will basically give some representation to words which are out of vocabulary or which were not there in the initial sentences, right? Now, let's move to this argument, which I was kind of telling you about, that we'll discuss this later. So this number of words equal to 100, it's literally how it sounds. That is, we are trying to give it the length, the tokenizer dictionary's length basically here. I think I've already showed from starting again, right? I don't think I can do it again. If there's a doubt, you can ask me. Okay. So this number of words equal to 100 thing, basically you get to decide here. I can say 50, I can say 1,000, I can say 10,000, I can say 1 million, whatever you think the tokenizer dictionary's length should be, right? We'll also discuss about this later, how, you should decide this number of words thing as well. But currently, when we are introducing the tokenizer object, we say, we basically decide the length of this tokenizer dictionary. So now for this, just one thing that, that could be a doubt is that what if in my training data, like basically the input sentences, which I'm using to convert to tokenizer dictionary, what if I have 101 words, let's say, right? So OV token will be given 1, right? And my tokenizer dictionary length I've decided, number of words equal to 100, right? So there can only be 100 words in the tokenizer dictionary. So now my tokenizer dictionary has first OV equal to 1, then, word 1 as ID 2, and so on. But I can, if the number of words is equal to 100, then I can only reach till word 99, correct? I can only reach till word 99. Now, what after that? What about the two words that are, what about the two words that are left after this? So we have only reached till word 1 to word 99. What about word number 100 and word number 101? Anyone? If I've restricted the tokenizer dictionary to 100 words, it can only occupy till 99 words plus OV token. Now, what about the two words that are left after this? OV, correct. They'll, since anything which is not there in the tokenizer dictionary will be associated to out of vocabulary. And this actually makes sense by the logic that we learned earlier. We learned that words are given in the priority of frequency of word and sequences, right? So basically the words, the word 99 and word 100 must not be that important because it is not occurring many number of times in the sentence. And if you see here, the only way we can get the meaning of the words when we are working with machine learning is by how many times or with what words it is occurring. By learning the pattern of what kind of words it is surrounded by, that is how the machine learning kind of grabs the meaning of the word, right? So if a word is not occurring that number of times, probably word 9 and word 99 and like basically the last two words are going to be of frequency 1 at best, right? So if words that are occurring only once, we anyways don't have much way to kind of grasp its meaning. Hence, it's better that we, treat it as out of vocabulary. Because we don't understand out of vocabulary words, and so we do not understand the words which are not occurring, so and so number of times. Vishesh, there's something very wrong about your question. Case sensitive is capitalization and small. right? Dog and dogs are two different words. Whereas dog with a small d and dog with a capital D would be something that you can ask case sensitive question on. Perfect. So this was about converting words to numbers. Now let's move on. Here I've basically implemented the same thing. We can ignore it. Now, we just saw that how we can, basically convert one sentence to a kind of numerical array. And we can even convert like a set of sentences. Like I want to convert this entire list of sentences to numerical array, right? So I just called tokenizer dot text to sequences, which is very understandable, right? Text to sequences. So the input is going to be text and the output is going to be sequences. That means numbers, right? So whenever I call tokenizer.text to sequences on any array of sentences, it is going to convert all the sentences in there using the tokenizer dictionary. And this is how it's going to look like. Now one thing is there that like we have it in a numerical format already. Now, before giving it to the machine learning model, what about the tokenization method where we tokenize based on most recurring characters like dog and dogs? Here, dog is taken as a token. I don't think I understand your question completely. Can you elaborate? It's pretty ambiguous, I'll say. If you want to unmute, I'm okay with that as well. Okay, great. Cool. So like I was saying that I'll just turn off the chat for a few minutes. So what I'm saying is that you have the numerical version of the sentences. Now for the machine learning model, you need to have a blueprint, right? So there is going to be a fixed length of input and there's going to be a fixed length of outputs. And it's not going to be like, in your machine learning model architecture was expecting, let's say 3 inputs, and you ended up giving it 2, thinking that, the one, if one is not plugged in, it is completely fine. So that's not the case. If the machine learning model expects 3 inputs, there are supposed to be exactly 3 inputs. Not lesser than that, not more than that. It's literally a blueprint, right? It will have, a fixed number of inputs and fixed number of outputs, and like basically think of it as a black box for now. And obviously sentences can't be of fixed length, right? I cannot make sure that, this is the project that I'm going to do. And all of the sentences that are going to be there in this project are going to be of length 10. No, I can't do that, right? So I need to make sure that I have a procedure to make all of these inputs of the fixed length. Okay. So for that, we use something called padding and truncation. Okay. We use padding and truncation. Okay. Again, padding and truncation is something that you don't have to define the function. You get it through TensorFlow, since that is what our masterclass is about. So let's say my ML model expects inputs of 4 as fixed length. Okay. Then if I have like basically input, I have sentence, input of sentence length, which is lesser than the fixed length. That is, fixed length is what was expected by the machine learning model. So if it is lesser than the fixed length, then I need to do something known as padding. And if the sentence length is greater than the fixed length that was expected by the ML model, then we are going to do something called truncation. Okay. So even if you understand the basic, English meaning of padding and truncation, it is going to be even easier for you, right? So padding is basically when, like, for example, you have a shoe, right? And if it is not of the same size as your feet, you're going to feel uncomfortable due to the space. So what you do, you pad it with socks, right? You pad it with socks, then your shoe becomes perfectly of the size that your feet needs, right? So that is exactly what padding is in English, right? And that is exactly what we're going to do here, right? If your sentence length is lesser than the fixed length, and what are we trying to, plug into the fixed length machine learning model, right? So to make it of that adaptable length, that is fixed length, we need to pad something. So how do we do that? Let's see. Let's say I have a sentence of length 3. Let's say true actually. 2 comma 4 is my input. Okay, this is my input sentence. Now, to make it of fixed length 4, I need to do something called padding, right? That we have already understood that if sentence length is less than fixed length, we'll do padding. So, what we'll do is we'll pad with zeros. Why zeros? Because 0 for sure is not associated with any word in our tokenizer dictionary. So there is no chance that any word is going to coincide with the ID 0. That is why even ML model will understand that this is not associated to any particular, any particular word, right? So that is why it's the safest option to basically use 0 for padding. Okay. Again, we can either do padding at the front or the back. So here I showed padding at the back. We can also do padding at the front, basically like 0, 0, 2, 4. Both of these possibilities are there. And you get to decide whether you want to do pre-padding or post-padding. Pre-padding as in front padding or post padding. That you can decide in your arguments. You can specify that in your arguments when, like I said, that you have TensorFlow object function for padding. In this function, you can actually specify whether you want to do pre-padding or you want to do post-padding, right? That is how the machine is going to do padding for you. That is make it of fixed length. Okay. Now, about truncation, let's say if I have an input of size, let's say 6, 2, 4, 1, 5, 4, 3. Okay. Now this this basically aligns with this, right? Sentence length is greater than the fixed length. Why? Because fixed length is 4 for machine learning model. So I have a 6 length sentence, but my machine learning model is only expecting 4 length, right? So what will I do in this case? I'll do something called truncation. Truncation literally means to drop something, right? And that is exactly what we're going to do here. Truncation. We'll drop some elements. Again, we'll have two choices, either to drop from the back, which is called post truncation. So you'll end up with this, 2, 4, 1, 5 post truncation, or we can do pre truncation. That is 1, 5, 4, 3. Right? In both the cases, I get a 4 length sentence finally. Either you can go with pre-truncation or post-truncation. That is about basically making, in tokenizer, we learned how to convert these textual sentences to numericals. Now, for these numericals to finally be plugged into the machine learning model, we need to make sure that they are all of fixed length. If they are not, what to do? If it is of lesser than fixed length, we need to do something called padding. If there are more, if they are of more length than that, then we are going to do truncation. In both of them, we get options for pre or post. Exactly. This is exactly the reason that we choose OOV as 1. Like I explained that we need to have zeros specifically for padding. Exactly. Truncation would definitely cause data loss, but that is kind of a trade-off that we, work with. In machine learning models, more the length that we are supposed to process, more will be the number of weights that we will be needed to update, more will be the connections. And so we'll require costlier compute, which obviously, very like it costs your company, it costs you. And so we need to reduce the compute cost. And so you need to decide with a trade-off of what sentence length you want to go with. I could make the sentence length, that is the fixed length, to 1 million, and then there might not be any loss, right? Even then there might be loss, but let's say, most of the sentences are of 1 million length at max. So let's say I have a data set which has 100 sentences, okay? And 99 of these sentences are in the range of 4 to uh, let's say 50 length. Okay. And only one of these sentences, a sentence, is of length 1 million. Then if I decide that the maximum sentence length is going to be my fixed length, that is 1 million, do you uh, do you understand how much loss these 99 sentences are going to make? Because all of them will be majority times padded, right? We are going to do only padding, and so that is literally waste. So you need to find out a trade-off between data loss, because if you have lesser fixed length, data loss is going to be there, and if the length is going to be more, then compute cost is going to be there. So we need to find a trade-off which does not hamper majority of the data loss or the compute cost. Okay, I hope it's clear. Perfect. Now we have done padding of sequences. Okay, again, like I said, we have TensorFlow keras. We import pad sequences function from it, and we'll do the padding. Now here I have not introduced fixed length or anything, though you should always, basically introduce max length and pre-padding or post-padding. But if you don't, then by default it is going to do pre-padding and basically no truncation. If you don't introduce the maximum length, it is going to assume that the maximum sentence length is going to be the fixed length. Okay. That is why when you are using a machine learning model, you'll always have a fixed length because you are introducing the architecture. And so you can introduce it here. We'll see it in the final, project code. Cool. So now we know how to prepare our data for finally being plugged into machine learning model. So now we are ready to introduce, basically start working on the actual project, that is sarcasm detection, like I was discussing earlier. Okay, here I'm just checking the version of TensorFlow that I use. Now, finally, let's start with the data set that we are going to use for the sarcasm detection. Again, you don't have to load it from any external source. If you run this through, storage Google APIs, you just have to run this code line, and your data set will be loaded temporarily, right? Let's try to print this data that we load from that link. So these are basically news headlines from a variety of news websites: Huffington Post, The Onion, and 2-3 more news websites. So what we have here is the article link from where we have basically sourced this, the headline of the news article, and the is sarcastic label, which is very important because that is exactly what we are trying to teach the machine learning model. Ki, this is the headline and this is sarcastic. This is the headline. This is not sarcastic. So now try to learn, from the pattern of the sentences of like basically you learn this pattern, and later on when you're done with the learning, if I test you on a headline, you should be able to tell whether or not this headline is sarcastic or not. That is why this label is very, very important. And that is why this type of problem is called supervised learning. That is, we are supervising it with some kind of label. That is, you have been given that this is the data and this is the label. Now learn it so that later when I give you the data, you are able to tell me the label of that. Right? So it is being supervised in some way. The learning is being supervised in some way. It has been given some direction. So this is called supervised learning. Right? So here in each data set, data point, data record, you have the article link, you have the headline, and you have the is sarcastic label. So if is sarcastic label is equal to, it has only two options, right? Like I said, it's a classification problem, sarcasm classification problem. So either it can be sarcastic or it cannot be sarcastic. There are only two possibilities. So if is sarcastic is equal to 0, that means it is not sarcastic. If is sarcastic is equal to 1, then it is sarcastic, right? So let's try to see one or two examples just to get the data. A former Versace store clerk sues over secret black code for minority shoppers. So this is not something which has been said in a funny tone. Hence, the is sarcastic label is 0. That means it has not been said in the reference to sarcasm, right? On the other hand, if I see this headline, mom starting to fear son's web series is the closest thing she will have to grandchild. This is something which is being said in a funny way or sarcasm, right? So that is why is sarcastic label here is 1. That means this particular sentence is sarcastic. Okay. So we have a lot of examples like that. You can go through the data set if you want to. Let's let's just start to work on how we are going to use this data set to finally use the learnings that we have done just now. That is how to convert it into numericals, how to do padding and padding and truncation, and try to kind of make it adaptable to machine learning model, then design the machine learning model architecture. So first step would be to make our data set in an acceptable structure. So we will basically only what we only have work to do with this headline and is sarcastic label, right? So we'll create two lists, sentences where we'll add the headlines, and the labels where we'll add the is sarcastic label, right? And this is how it's going to look like. I've just tried to print two rows of it, sentences and labels, and we can see it. It is printing all right. Length of the sentences and labels, how many records do we have that we are trying to work with? It's 26,709. Okay. Now, finally, we'll start to work on this data. These are some variable values that I've initialized. I'll keep on coming back whenever I reference them in the code. Okay. So firstly, we'll try to split this data set that we just saw, like the 26,709 records, into training and testing, right? So I've decided with a length of training size 20,000. So 20,000 rows will be my training data, and the rest of the 6,709 will be my testing data set. Now for basically training data set and testing data set, in case you don't understand the reference, training data and testing data is exactly like it is sounding. Training data is basically how you study for the test that you don't know what is going to come in the test. You're just trying to learn and better your subject knowledge, and you know the questions and you know the answers to it. That is how you're trying to learn the subject. And in testing data, it's basically an exam that you'll give to kind of verify whether or not you have learned the subject or not, right? So testing data is going to be something which will only have questions and you will have to give the answer to it. Similarly, the here questions are data and answers are labels, right? So in training data, you have the labels, and you try to learn from it. You try to gather all the patterns. You try to update your parameters to learn those things. And then in the testing data, you'll only be given the sentence, and you'll have to basically machine learning model will have to predict the label for it, that whether or not this data is sarcastic. So we have split the data set into 20,000 and 6,709 as training and testing data. Both these are training sentences, training labels, testing sentences, testing labels, right? Okay. Now, what is going to be our steps? We have the sentences. We'll convert it into numericals just like we did earlier. Then we are going to do padding and truncation to make it of a fixed length. And then we are going to give all these fixed length numericals, numerical version of these sentences to machine learning model. Okay. So now firstly, let's introduce the tokenizer object. Tokenizer object, we have two arguments that we have learned earlier, number of words and OV token. So number of words will be equivalent to vocabulary size that I have initialized here as 10,000. So the tokenizer dictionary's maximum length can be that of 10,000, right? And OV token to take care of, data or words which have not been referenced or which did not make it to the tokenizer dictionary, right? Tokenize, then finally, like we saw that we'll do tokenizer.fit on text on training sentences only, right? Because training sentences is the only thing that we are supposed to know, not the testing data. So we'll fit the tokenizer on training sentences. So that means that we'll gather all the words that are occurring in the training sentences. And in the priority order, tokenizer is going to create a tokenizer dictionary with OV token and the top 10,000 words, right? This we do not need here. Okay. Then we are going to do the same thing that we did earlier. In this first line, what we are doing is, okay, sorry. So we are converting training data sets or training sentences to numerical. So we'll use tokenizer that we just trained here, tokenizer.fit on text, right? We have the tokenizer now. It has assigned a word to ID thing. Now we call that tokenizer and we ask it to convert text to sequences for the training sentences. So here all the training sentences have been converted into numerical. And next we are going to pad it to be a fixed length that we are planning our machine learning model to have, right? So the sentences that I'm trying to, or the arrays that I'm trying to pad, training sequences, max length is something that, that is a fixed length that I'm going to assign to the machine learning model to have as an input. Max length I've initialized here again as 100. So the input sentences can be of maximum length 100. That is how the padding and truncation will be done. Then padding is equal to padding type and truncation is equal to truncation type. So padding type and truncation type, both I have initialized as post. Okay. So padding will also be done post padding and truncation will also be post truncation. So basically pad sequences, what it does is it will take all the training sequences, which is basically training data set converted into numericals using tokenizer, and it will pad and truncate to make it of the fixed length, that is 100. Okay, same we'll do with the testing data set. And now we have training and testing sentences converted into numericals, done padded and truncation, and now it is ready for the ML model. This is a sample of how your, like one of the sentences is going to look like. So the sentence initially was, North Korea praises Trump and urges US voters to reject dull Hillary. So based on the tokenizer, it has converted North to 226, Korea to 477, praises to 2843, Trump to 13 and to 9 and so on, right? And since the fixed length was 100 and this was obviously not of 100 length, it has been post padded with zeros to make it of length 100. So this entire array is of length 100. Okay. Great. So this is the entire training data set that is going to look like. All of these arrays are basically 100 length, post padded with zeros. Now, before giving it to the ML model, we are going to convert it into NumPy arrays. Okay. Why do we need NumPy arrays exactly? Again, something which is not relevant to this project, but I still thought that I'll tell you about it. So let's talk about normal arrays and then compare them to NumPy arrays. So normal arrays in Python, again, I'm being very, very specific to Python here. So in normal arrays in Python, you can have elements of literally any data type. Okay. Basically, here's this list. Okay, you have 1, comma 2, comma 5.3, comma string, comma integer, comma float, comma object, any kind of object. Basically, you have a class, you define an object inside it. So basically, the gist being that any data type is allowed in less in Python. So what happens in the storage part where you are storing this in your system? You have the list. Then for each and every element, you have to store the value, that is 1, along with the data type of that value, integer, right? Then again 2, and 2's data type integer. Then 5.3 float, string, 7 int, 9.2 float object. So basically you have to store a lot of metadata. For each and every element, you need to store some metadata here, right? So it is taking up a lot of storage. For each and every element, if I'm storing the value as well as the metadata, it is taking up a lot of storage. And when we are talking about machine learning models, I'm sure you're aware of it, that we try to work with like millions and millions of rows, right? So we need to make it optimal, right? That is why we come to NumPy arrays. NumPy arrays are only allowed to be like all the elements in the NumPy array are allowed to be of the same data type. Either they can be all of integer, or they can all be float, or they can all be string, right? Um, so only one metadata is stored for the entire list rather than metadata for each and every value, right? So this basically saves us a lot of storage, and it might not affect that much when we are talking about these small arrays, but it makes a lot of difference when we are talking about say millions of rows. Even here we have like 26,709 records. So storing metadata for each and every value will only make the process slower. The lesser the storage, the faster the computer is going to be, right? So that is why it is a good practice that uh, before using it with the machine learning model or giving it to the machine learning model, we convert it into NumPy arrays. Okay, I hope you got this. Rishabh, what part did you not get? Like, even if there are million, like basically, let's say it's of 1,000 length, and all of them are of integer, still, since it is allowed to have any data type, it is going to store the metadata for each and every element, right? It is not going to just assume that everything is going to be of an integer type. Whereas in NumPy arrays, everything is going to be of the same data type. Hence, we store only one metadata instead of metadata for each and every value. Is it clear? Exactly. Is it not making sense here? Great. Now, finally, we have our data and everything. Now we'll finally design our model architecture for these sentences and corresponding labels to be learned by the model, the patterns to be learned by the model, right? Again, using TensorFlow Keras. Using TensorFlow Keras, we are using the object sequential. In sequential object, basically what you can do is you can give it a list of models that you want to layer, and in what sequence you want to layer the models. You can literally just list them like an array or like a list, and it will basically assume that you have an input. It will go first to this layer, then the output will go to this layer, then the output of here goes to this layer, then the output of this layer goes to this layer, and so on, right? So that is why we have used sequential. If we wouldn't have used sequential, we would have to introduce each and every layer separately, that this layer takes the input and this is the output, then use that output variable to kind of initialize this layer, and so on. So sequential works better for us. We can just give a list of models, and it works sequentially, right? So layer 1 output goes to layer 2, layer 2's output goes to layer 3, layer 3's output goes to layer 4, and the final output comes out. Okay. So don't get too confused about these layers. We are going to discuss each one of them. So for the we have first layer that we are going to use is embedding layer. Second layer is a global average pooling one-dimensional layer. Third is a dense layer, which is basically a neural network layer. And again, a dense layer, which is a neural network layer with 24 neurons activation ReLU with one neuron in activation sigmoid. Let's try to discuss this in detail. I'll share my OneNote page to explain this. Okay. Are you able to see this whiteboard that I've shared? Okay. So here we are trying to understand the ML model architecture of like what we literally just introduced. Okay. So first layer is the embedding layer. This embedding layer has, I'm switching off my chat box for now to avoid any disturbance. Embedding layer has three arguments: vocabulary size, embedding dimension, and input length. Vocabulary size. Our vocabulary size is what? 10,000. Then embedding dimension is 16 that we've initialized here. And our maximum length is basically the input length, is going to be of size 100 like we saw. Okay. Now the second layer that we are going to have is global average pooling one-dimensional layer. Third is a dense layer with 24 neurons and ReLU activation function. And the fourth layer is a dense layer with one neuron and sigmoid activation. Okay. Let's start with the first layer. That is this embedding layer. Embedding layer has vocabulary size 10K, embedding dimension 16, max length 100. So what is exactly embedding, or what is meant by embedding? Sorry. Embedding means that we are trying to, like, if trying to basically represent the meaning of each and every word, right? Now we have already converted words to IDs, right? What that was exactly what was tokenizer was doing, right? Ki word one ko one de diya, word two ko two ID de diya, and so on, right? But these one and two are not meanings of this these words, right? They are just numbers that we have assigned to them, just like a key or just like a name, exactly, right? But we don't know what these words do or what are the meanings of this. That is exactly what embedding layer is going to do for us. It is going to create a representation which is going to represent the meaning of all of these words, right? Now how is it going to do this? Let's see. It is going to create a matrix of vocabulary size, that is 10,000, by embedding dimension that is equivalent to 16. So basically, what is the vocabulary size exactly? Each and every word in the tokenizer dictionary, right? So these are basically, you can understand, these are the only list of words that can, words or word representation that are possible in our input sentences, right? So word 1, word 2, so on, word 10,000. These are all the words that are possible in the input sentences. And for each of these words, we are trying to create a meaning representation in 16 dimensions. Again, it's going to be numerical, obviously. So we are going to have like E11, E12, so on, E116. So this is the 16 dimensional or 16 like length meaning representation of word 1. Similarly, E21, E22, and so on, E26, right? So this is going to be a matrix which will basically get the corresponding meaning for each and every word. Now, how does it do it exactly? Like, obviously, it's a black box model, but still we need to understand how is it doing it, right? So initially, when it has not seen any sentences, how is it going to learn these embeddings or meanings of the words? Just let's not use the word embedding. Let's use meaning, right? This is meaning representation. So how does the machine learning model try to learn the meaning of the words? That is based on how, like, what is the extent of meaning that these sentences are trying to explain to this machine learning model is, to the extent that we can get the sarcasm label, right? So we are trying to use the training data set itself to learn these meaning representations, right? Now, first let's try to understand conceptually ki dimensions का क्या meaning है, मतलब embedding dimension when we are saying, why are we using multiple numbers to represent one word, right? Now, I will take a short example of this. Let's say a song. Like basically a song, how can it be represented in multiple dimensions? You can represent it using, its danceability, if that's something, I don't know. Its pitch, right? At what pitch the song is there, a numerical representation of that. Then how many likes did it get, right? So how much loved is it? And, there are a lot of like, audio frequency or whatever, representations are there. And that is how you can represent a song using numbers, right? And more the number of dimensions, that means more features are being grasped to kind of define this song. So you can understand that higher the dimension, that means uh, the details are captured even more, right? We are trying to understand the meaning of the word even better. And if the dimensions are lesser, then there, the differentiability between two songs is going to be much, much lesser, because there can be multiple songs with the, same two features, but there will be lesser similar songs with, let's say 5 common features or something, right? So with this concept, you can understand ki more the number of dimensions, that means more, better is the capture of meaning that we are trying to do, right? And lesser dimensions means lesser meaning is being captured. So that is how you can understand the concept of dimensions here. So we have decided with a, decent dimension, that is 16. Since our motive is basically just to do binary classification, right? Binary classification means we just want to understand the words enough to kind of classify the sentences as, sarcastic or non-sarcastic. Now, how does it learn these words? This E11, E12, E21, whatever I've drawn. How does the machine learning model learn these words? Initially, these are randomly initialized, right? So let's say this is 0.23, this is 0.51, this is 0.62. And randomly, like using a random number generator, they are initialized, right? 0.61, 0.31. Actually, not just this embedding thing. Any machine learning, if you have understood machine learning models mathematically, you would know that initially, before the data set has been introduced to the ML model, initially, they're all the weights or all the parameters are randomly initialized. So is the case here, right? So now, when a sentence comes, we already have numbers here, right? They are just random. They are not based on the input sentences that we have. Now let's say I received the first sentence. Okay. Sentence has how many words? 100 words, right? So let me say I1 because we'll get confused otherwise. I1, I2, I3, so on, I100. Right? 100 length sentences, all of these are 100 length sentences, right? So now what happens? We'll take this I1. We'll find this I1 here in the embedding matrix. It's literally like a lookup. Key, this is ID, let's say 62. So I look up in this embedding matrix. Let's say here is the word number 62. I'll capture the meaning of the word through the embeddings here and I'll paste it here. So you will get like E62.1, so on, like the basically the 16 dimensional embedding, right? Similarly for I2, I look up the ID here and corresponding dimension, corresponding embedding, I'll paste here. Same for I3, same till I100. So now I have a matrix of size 100 by 16. Okay. This 100 by 16 matrix goes to layer number 2, goes to layer number 3, goes to layer number 4. And finally, after layer number 4, you get the label, right? Or the score of sarcasm. What was our main motive in the output? We wanted to get a score or probability, let's say probability of sentence 1 or the input sentence, since I'm talking about only sentence 1 right now, probability of sentence 1 of being sarcastic. Okay. Let's say the probability that we have predicted is, let's say 0.3. Okay. Now, when we are using training data, we have the correct label and this is what we have predicted. So let's say the correct label was 1. We had I hope you're getting correct label, right? The is sarcastic label that we were using to train the model, right? So this is the true label and this is the one that we have predicted. Okay. Now you see that this is more close to 0 than 1. That means our model's parameters are off. They're not working well. So what we'll do, we'll try to find the loss, and that is how we'll assess how the model is doing on currently, at current sentence, right? So the loss is basically true minus predicted. Like what is the difference between what was supposed to happen and what has actually happened, right? So if you see the, loss comes out to be 0.7, which is very high, right? So this loss will now back propagate. Back propagate, if I tell in human languages, basically that at the production level, like basically we're creating a product, the product has gone to the customers and the customers have given review. Now, if the customers' reviews are very off, right, like they are very, very negative, then more updates are going to be done in the production cycle, right? More updates are going to be done in each and every layer so that later on, like basically updates are being done in the parameters of all of these layers. What are the parameters in embedding layer? These numbers, right? So these numbers will be updated now through loss propagation, right? Now, sentence 2, when sentence 2 will come, it will get the updated embeddings, right? Then again, these updated embeddings will, form this 100 by 16 embedding matrix, right? It will go to layer 2, layer 3, layer 4, and finally you'll get the probability of that sentence 2 being sarcastic, right? Let's say that is 0.5, let's say 0.5. So this time the loss will be true minus predicted 0.5. So obviously better situation than the last time, but still bad, right? Again, this will back propagate, right? And updates will take place so that in the next iteration, things get better than they were previously, right? That is how the parameters of any machine learning model gets updated through training or through looking at the actual, data set. This is exactly like you are learning the syllabus right? You learned a question, you're revising a question, then you saw the answer, how much off it was from your answer, and then you learn more or less based on how off you were on that particular topic, right? That is exactly how ML model learns as well. Right? I hope you got the gist of this. This is exactly how embedding layer is going to work. It is going to form an embedding matrix where you will have for each and every vocabulary word, you will have a 16-dimensional representation of meaning. Every time a sentence comes in, it for each and every word that it has, it will draw the embedding or representation of meaning for that particular word from the embedding matrix, and that it will do for each and every word that is there in the sentence. Then this output will go through all the layers that are there in the ML model, which we'll discuss just after this. And then finally, at the output, you are going to get the probability of that sentence being sarcastic based on the probability that we have predicted versus the actual label that is there in the training data. We'll find out the loss, right? How good or bad our model is doing. Based on that, the magnitude of good or bad, we are going to make updates. So let's say the loss is very less. That means our model must be doing something very, very right, right? So we need to make lesser or, lesser magnitude updates. थोड़ा थोड़ा अपडेट करेंगे उस टाइम पे. But if the loss is say very large, then the magnitude of updates will be larger as well. Okay, that is how embedding layer works. Is it clear? Okay, perfect. Mayank is saying why to set random dimension. It can be initialized with zero point 0.0 at first. Uh, do any of you know why we won't do that? Why are we randomly initializing and not doing all of them at 0 0.0? Any clue? Anyone? Anyone wants to take a guess, maybe? Not because it won't backpropagate, no. Exactly, it is going to cause more chaos. Like you'll assume that random values are going to give more chaos, but you have to understand that these values are supposed to reach somewhere that we don't know. It could be very high from zero, or it could be very close to zero as well, right? We don't know where it is going to go. So for a safe side, so that it is somewhere in the middle or somewhere random, that the adjustments that are supposed to be made are not that high of magnitude. Like I said, that loss when it backpropagates, that makes the updates, right? So the magnitude of the updates is dependent on the loss itself, right? So it is not going to vary ki, for this we need to make bigger updates, for this we need to make smaller updates. No, all of them will be updated once the loss back propagates. So it's safer to kind of use random values rather than having a fixed value, because all of them are going to go through different values. Like the ultimate, once the model is trained completely, the values are going to be, some are going to be high, some are going to be low based on how the representation is created. So it's safer that we use random values rather than like 0 0.0 or 1.0. Okay. When I say meaning of the words, it's the meaning of the words to the extent that we're able to represent, basically uh, find out the probability of that sentence being sarcastic. It's not like literal meaning. That is just an example or a form of speech that I'm using to kind of basically explain embeddings. It is going to give it a representation. Let's talk it like that. For example, when I'm learning words in English, I try to I understand words not by their spelling, but by the meaning of them. Like, let's say chair. I understand it through whether, I can sit on it, I can use it as a furniture and all those things, right? So that is the representation of the chair. Here we are using the words to represent them numerically to, to the extent that I'm able to correctly find out the probability of them being sarcastic. But could this randomness cause two word dimensions mostly similar for poles apart words? Definitely. It will only happen. Like I said, it is not actually representing meaning, but it is representing the words to an extent that I am able to classify sarcasm. So let's say if I have two words, let's say A, B, C, like just understand these are words, okay? Like A, B, C, D and A, G, C, D. And both of them, and let's say there are more words as well. A, B, C, G. Okay. And let's say all of these sentences have sarcasm label as 1. Okay. Then whatever understanding the embedding matrix is going to make through this is that B and G are very, very similar. If this is happening very frequently in other sentences as well, or in the majority of the sentences, or wherever B and G are used, then, and all of them have the same label, right? So that means B and G have the same impact on the sentence to decide the sarcasm label. So then B and G will be treated absolutely same even if these words are poles apart. So actually, thanks for like asking that question. It is a very good explanation of what representation of the words mean in this current project. Are you able to understand this? We are not trying to exactly get the meaning of the word, but we are trying to get the representation of word to the extent that it like how much involvement or how what is the impact of that in deciding the sarcasm label. Okay, let's move on. Let's move on to the second layer, which is like the explanation of this will be super quick. Second is global average pooling one-dimensional layer. Second layer is global average pooling one-dimensional layer. Okay. So why are we using it? I'll tell you on the third layer. Basically, the output will go to third layer, right? So third layer is the one that requires an input in one-dimensional. Ignore that for now. Let's try to see what global average pooling one-dimensional layer does. Exactly how it says key, what it's going to do is it will take the input from the first layer. What is the input from the first layer? Sorry, output from the first layer. It is this 100 by 16 matrix that is formed using the embedding matrix. है ना? So this will go as an input to global average pooling one-dimensional layer. And what this will do, we have 100 by 16 layer as an input. Now, global average pooling layer, what it will do is for each and every column that we have, for each and every column, it is going to find the average and form a matrix of average of all of these 16 dimensions like A1, A2, A3, so on, A16, like this, right? Let's look at an example, obviously not of 100 length, but a small example of, let's say, 3 by 3 matrix. So let's say this is 2, 3, 1, 1, 1, 8, 6, 6, 3, let's say. Okay. So if I apply global average pooling 1D layer on this, it is going to look like this. For each and every column, we are going to take the average. That is for this layer, let's say the average will be 2. For this layer, let's say 10 by 3, average will be 3.3. Then for this layer, 6 to the 12, 3, 15, 5. Okay. So the output of global average pooling 1D layer will be this. Okay. If you give this as an input, you're getting this as an output. So similarly here in 100 by 16, if we put the global average pooling 1D layer for each and every 16 dimensions, we're going to find the average throughout the elements. And this is how your output is going to be going to look like. It is going to be a 1 by 16 array. Okay. Is this understood? Global average pooling layer? Great. Let's move on to the next layer, which is something which is widely known. Dense layer. Like I said, it's basically a neural network layer. Have you guys heard of neural networks? Okay. Um, so do I need to explain neural network layers, or uh, like you guys are good with it? Okay, I'll try to explain it in a summary. What does that average is representing? What does average represent anyways? It's trying to summarize the data, right? When you say the average of scores in the class is this much, let's say 50, what is it representing? It mean is just another word for average, right? Yeah, summary. Exactly. It is trying to summarize the data points. So basically, our main goal, global average pooling, why did we use it? Well, I know it's causing data loss, obviously, but we use it because our next layer is neural network layer. And neural network layer needs its output only and only in one dimensional layer. And if you see first layer is very, very important because like before first layer, we don't have any uh, representation of the word's actual meaning, right? So here we need to find out the meaning of the words, and so we have created an embedding matrix, and so we get a matrix of 100 by 16. Now this 100 by 16 matrix can't go into neural network layer, and neural network layer is important because neural network layer is uh, a deeply connected machine learning model which has multiple layers. And why multiple layers? Because each layer is kind of trying to learn patterns in different dimensions, or different dimension would be right. So so for this data to be given to neural network layer, which is obviously very important in this project, we are trying to do a transition that we do through global average pooling 1D layer so that we get an output of one dimensional, right? So that is why we used it. Is it clear? Okay. Cool. So I will only take 5 minutes to explain this because we are on a clock right now. So basically, neural network layers are where you have inputs, right? You have layers of neurons, right? And basically, each neuron in every layer is connected to every neuron in the next layer, like this. Right? Every neuron is connected to every neuron in the next layer. And this is the output, let's say. Okay. So let's try to zoom into one of the neurons and try to understand what each and every neuron is doing out here. So let's say these are my inputs, x1, x2, x3, and these are all going into this neuron. Obviously, same thing is happening with all the other neurons, but let's try to understand from one neuron's perspective. I've just zoomed into this if there's any confusion. So for each and every connection that you're seeing here, each and every connection, like this, every connection has a weight associated with it. What is weight exactly? A parameter. Just like we had these embedding matrix numbers as parameters, right? We're getting updated by backpropagation of the loss. These weights are also such kind of parameters which will be updated based on the loss that is backpropagated at the from the output, right? So again, these work in the same way. They are randomly initialized initially, and based on the learning or based on the backpropagation of the loss, they keep on getting updated, right? As and when they're learning more and more. So I'll just represent these using W1, W2, W3. These are different weights for this particular neuron. So the output that the neuron is going to give is going to look like a weighted sum of all of the inputs, like W1x1 plus W2x2 plus W3x3, right? And plus a bias, okay? Because obviously when you take a weighted sum, you take a bias along with that. And what is actually unique here is that along with this weighted function, we have an activation function on top of this. This activation function is always non-linear. Now, why is it non-linear? Because our main concept that we wanted to have a neural network was so a neural network you can understand like how neurons are connected in our brain, right? So for example, this is my brain and like this is I, and I'm seeing an apple, right? This is my hand, let's say. So whenever I see, okay, my neurons from the eye send signal to the connected neurons, and so the neurons reach to my brain, and then my brain finally gets triggered. It takes a decision, it gets activated, and it activates neurons connected to it, and then it activates neurons that are connected to that, and so on, right? And finally my neuron gives the signal to my hand to kind of hold that apple, right? That is exactly what we are trying to replicate in neural networks. That is exactly what we're trying to do. So why so many layers exactly? Because each and every layer is trying to capture some pattern from the data. And when we have such complicated problems like sarcasm detection, we try to use deep learning layers because normal linear layers do not have the capacity to capture so many complexities in a sentence or in a data set, right? So that is whenever you have some complex patterns that you're supposed to capture, you'll always use neural network layers, right? So now in this, for each and every neuron, it takes the weighted sum of all the input neurons that are there. And on top of it, to activate that, you put in a non-linear activation function on top of it. Why non-linear? What if I use linear activation functions on each of the neurons? What will happen then? Considering this happens at each and every neuron, what will happen then? Like this is my inputs, these are my neurons, and this is my output. What will happen if I have linear activation function on all of these neurons, and let's say I have like thousands of these layers? Anyone? The output not would not be probabilistic. I mean, I don't know what to get from that sentence. But basically, if I take linear, put a linear activation function on all of these, then ultimately your output is going to be a function x1, x2, x3 only. That means it is going to look like this. Finally, however, let's say if I even put 1 million layers there and each of these layers have like, let's say 1 million neurons each, like each of these layers have 1 million neurons each, and more the complexity, more the neural network is supposed to capture the complexity. But if you put in linear activation function and even if you put too many layers and too many neurons in each layer, the ultimate output is going to be a linear function of the initial inputs. So basically, this is going to look like this: AX1 plus BX2 plus CX3. So if we had to do this ultimately, we had to, just have a linear relationship. Why did we add so much complexity and increase the compute? This could have been literally just one neuron, right? So obviously we don't want that. Why would we add complexity if we don't want to capture the complex patterns in the data? That is why it is necessary that we only use the non-linear activation function. Now, even in this non-linear activation function, we have choices to make from. There is sigmoid activation function, there is tanh activation function, and there is ReLU activation function, right? Yeah, Himanshu, it would be predictable, correct. So sigmoid activation function goes like this. Basically, you get a, sorry, 0 to, you get an output between 0 to 1, right? For tanh activation function, you get a value between -1 to +1, right? And for ReLU activation function, basically you get a non-negative output. That means for ReLU of X, let's say I want to put ReLU activation function on something called X, then it will basically be max of 0, X. That means if X is negative, the output is going to be 0. If X is positive, then only then it will be equivalent to X itself. Now, obviously, we can play around with all of these activation functions in different neural network layers, right? But for the output layer, you need to be mindful of what activation function we use in the final output layer. It is based on what kind of output you want. Like, for example, if I want an output that, is kind of a probability score, right? Then I would choose sigmoid activation function. Why? Because it gives an output in the range of 0 to 1, and that is exactly what probabilities range is, right? And this exactly suits my current problem that I'm solving, that is of binary classification. I want the output between the range of 0 to 1, which is the probability of the sentence being sarcastic. So then in the output layer, I'll use sigmoid, and that is what we are using even in the machine learning model definition. Then wherever I'm okay with minor negative values and positive values, like for example predicting the temperature or something like that, I can use tan h as the output layer, right? And if there is something where output can only be a positive value, for example, when I'm trying to predict the price of a house, right? This can never be negative, right? So in that case, I can use ReLU activation function in the output layer. For the internal neural network layers, we can play around. We can use any activation function, and we can try to see which one is trying to capture or is capable of capturing the complexities at its best, right? So the third layer is dense layer, that is neural network layer with 24 neurons and ReLU activation function. And the final output layer is of 1 neuron and sigmoid activation function. Just now I discussed that why sigmoid activation function, because in output I want the probability score of the input sentence being sarcastic or not, right? So just to summarize, our first layer that we are using is embedding layer. In embedding layer, we have 3 arguments: vocabulary size, embedding dimension, and maximum length. What does embedding layer exactly do? It creates an embedding matrix where for each and every word that is there in the vocabulary, we try to give it some representation, right, of size, embedding dimension. And more the embedding dimension size, more representation is embedded. Lesser the size, lesser depth of the word's meaning is embedded there. But we need to decide with a trade-off. We can't have too high embedding dimension size, otherwise uh, our our problem becomes much more costlier, because the size of this output matrix increases, and so does these parameter size, right? As you know that after backpropagation, we update these parameters. So more the number of parameters, more work we have to do, more cost it is going to incur, right? So that is why we need to find a trade-off in this embedding dimension. Then finally, through these, whenever we receive a sentence, for each and every word, we find the corresponding embedding. Finally, we get an output matrix of size 100 by 16. We give it to the global average pooling one-dimensional layer, which basically takes the average, tries to summarize each and every column using averages, and it gives me a 1 by 16 one-dimensional layer, which is basically average of each and every column. Then once we have this one-dimensional embedding, we give it to the neural network layer of 24 neurons and ReLU activation function, and finally we get a dense layer of 1 neuron and sigmoid activation function. Why sigmoid activation function? Because ultimately we need an output in the range of 0 to 1. Okay, so this is the summary of our entire model. Let's move back to our code. So we have already learned this. right? We take embedding layer, we get an output of 100 by 16. 100 by 16 goes into global average pooling layer, we get an output of 1 by 16. Then we go through dense layer, we get an output of obviously 24 one dimensional. Then dense layer, again one neuron we have, we get an output one number between 0 to 1, right? Now, how are we trying, how will we compile this? Compiling is exactly what I was showing, right? That, how do you train the model exactly, right? So I'm training based on the loss. What will be the loss computation strategy? That is also very important. For example, in binary classification, we use binary cross entropy loss computation. I have written the formula as well here. P log P plus 1 minus P log 1 minus P, right? So we compute the binary cross entropy loss, and based on this binary cross entropy loss, we backpropagate and update all the parameters that are there in the model using the optimization strategy Adam. Adam is basically the most up to date optimization strategy that we use in normal machine learning models or deep learning models, right? And the matrix that we are trying to optimize on is accuracy. Accuracy, that means what is the percentage of times that my model is going to do predict right, right? So this is my model architecture completely. Now, I've just tried to print the model summary. If you call model.summary, it is going to give you a kind of summary of what all layers you have used, what number of parameters are there in each and every layer, and everything. It will give it to you, right? Now, finally, the model training part, right? So in this model training part, let's look at the function. We call model.fit here. Model.fit on the training data set that we have already padded and made it adaptable to machine learning model. We give it to the model. The training data, training labels, epochs. What is epochs exactly? It decides how many times you're going to show the training data set to the model. So basically, like, you'll show it one time, it will obviously update its parameter, then you show it another, retrain it on that same data set again and again till it is able to upgrade its parameters and like basically reach to a level where it has learned enough, right? So we are using 30 number of epochs here. And the validation data is going to be the unseen data set, which we have decided with the testing data set. Like, we split the data, right? We'll use 20,000 for training, 6,000 for testing. That is exactly how we are going to validate. Validate as in how well our model is actually doing. Because training data, it has already seen. So it is obviously going to do better at that. But what about the unseen data is what basically tells how well you're doing at the model. So epoch, for example, like this, like I've tried to fit the model, and this is the performance that it is printing. For each and every epoch, it is going to tell me what is the loss, what is the accuracy. That means what percentage of times is my model predicting right. And this is for the seen data set, that is training data set, something that it already knows about. And this is the validation loss and accuracy, that is performance on unseen data, right? So you can see, if we look at the training performance, you see that it keeps on increasing after every epoch. Why? Because it is seeing the same data set again and again in every epoch, right? So obviously it is going to know it better and better every time. And ultimately you get an accuracy of 99.32% on the seen data set. But again, we like whatever nodes we are studying from, if we take tests from the same data set that we have already seen, then it is not a good verification of how well you're doing. The verification that you do how well a model is doing is through the validation data set, which it has not seen yet, right? So if we see the validation loss, you see that it's not increasing as better as training data. It's 74.88, 83.78, 85.32, and so on. And you can see that there are a few dips here and there as well. That is, it did really well at epoch number 7, but it did a little less better in epoch number 8, right? And your final, like finally, the highest accuracy that we were able to reach here was 85.5%, which is pretty good, right? 85.5% is what we are able to get to. For verbose also, I've explained it here. I'm skipping that for now. It's just how you want to, print the performance. It has nothing to do with the ML model. Okay, now let's try to test how well our model is doing. Okay. So here are two sentences that I'll try to test my model on. Granny starting to fear spiders in the garden might be real. Okay. And the second sentence is Game of Thrones season finale showing this Sunday night. So we are expecting that this should be sarcastic, right? Because it does look sarcastic, right? So the label should be closer to 1. And here, since it's something which is factual news, the sarcasm label of this should be closer to 0. We adapted it to the same format that we did for all the other data points, right? And then we finally gave it to our model to predict, the model that we just trained here, right? Let's see. For the first sentence, we are getting a probability of 0.9. This e power minus 1, you can relate it to 10 power minus 1 itself. So 9 into 10 power minus 1 is 0.9. So 0.9 is very close to 1. That means we are doing very well here. And for the second point, second sentence, we thought that it should be closer to 0 because it is non-sarcastic. And here we can see that it is 1 into 10 power minus 5, which is like 0.000001. And so we can see that our model is working well on at least these two sentences. And we have more sentences here to test our model on. And let's see how it has performed here. First sentence is, I'm myself a king of my state. I'm myself a king of my state. The sarcasm label that we are getting is 1 into 10 power minus 9. So it is predicting it as non-sarcastic. Again, there can be, like we have seen, the accuracy is 85.5%. So it is still has almost 15% chances of going wrong as well, right? So you will see some, flaws also, like basically wrong sarcasm detection as well. Then here, code was shared in mail or in this chat. It's just a simple question. It should not be sarcastic. And it's not. It is 1 into 10 power minus 6, which is pretty close to 0, right? This session was amazing. Again, something which is not being said in a sarcastic tone. 1 into 10 power minus 6, very close to 0. Then data engineering is better than data science. Some kind of an argument, I'll say. Again, it's very close to 0, 8 into 10 power minus 11. Then poor man becomes PM. This is something which can be said in a sarcasm-like tone. And so you can see that our model is predicting correctly as 0.9. 9 into 10 power minus 1 is 0.9, right? Then there is another sentence, you are bald enough to have a haircut. Again, something being said in a sarcastic tone. And let's see what score it has predicted. It's 0.6. So it is closer to 1, I'll say. Then my friend is going to lose. I don't know if it is sarcastic or not, but our model says that it is. So it is predicting as 0.9. Then your posts are becoming too frequent these days, something which is being said in a normal conversation. And the score that we have is 4.4 into 10 power minus 8, which is very, very close to 0, right? So this is it about our project here. And we are able to create a model which works with a good enough accuracy of 85.5%. Now I am ready to take any doubts if you guys have. While doing padding and truncation, is there any optimal or smart way to handle data loss or compute loss, or it needs to be done manually only by looking at the test data? If you're talking about deciding the maximum length, then yes, you need to find out, like basically you can try to test, try to print a graph of, how frequent is what length, and try to decide a length where majority of the sentences are safe from data loss. But obviously we'll have to compromise a minority of the sentences, but at least your majority should be saved, I'll say. That is how you can go on with deciding the maximum length. We are predicting the level of sarcasm in this model, or classifying whether a sentence is sarcastic or not sarcastic. So here we are just predicting the probability, and what you can do is we can add another layer if you have to get only 0 and 1, like is it sarcastic or not. You can just write a quote that if this probability is closer to 0, that is less than 0.5, predict 0. If greater than 0.5, predict 1. I think I told it very clearly. Epoch is basically showing the entire training data uh, to the model one time. That is one epoch, not one sentence. How do we decide the number of neurons? Is it definitely trial and error based, and based on how much complex do you feel that your data set is? So you should try to, again, your main goal or main priority should be key. The cost should not exceed a lot, right? So you can start with small numbers. If you're able to do good in small numbers, then it should be good enough. If not, then you can obviously increase the number of neurons and number of layers as well, right? You understand that each and every connection that is being created, and uh, there is one connection for a connection between every two neurons in two consecutive layers, right? Every neuron in one layer is connected to every neuron in the other layer, and each of these connection has a weight associated with it. And the more you increase the number of weights, and basically whenever you increase the number of layers or number of neurons per layer, the number of weights that are supposed to be optimized will increase, and so will the compute cost. Srihari, I've explained this already. Ma'am, can you explain some resources or books where I can train myself in how I use Kaggle a lot for learning purposes. If you want, like in my initial days, even I used Kaggle because you have access to data set plus discussions, and people who are good at it, they have already solved these competitions. This topic was definitely not about data imbalance. That is why I skipped it. But definitely you can, test for data imbalance as well. And if you feel, you can solve it by undersampling or oversampling. Thank you, guys. Hyperparameters in this model, you will have to, elaborate at least a little bit. I don't know what to get from this. No, I cannot actually. Boss Code Academy will be sharing this code with you directly. Thank you, Imanshu. Thank you so much. Thank you, guys. I'll just share the Google review link. Any other doubts that you guys have, you can ask me. You'll have to ask that to the representative who'll get connected with you. Some idea on how to take a model which is already. What are you asking? How to take a model which is already pre-trained and using the weights to retrain. Um, I mean, how can I give an opinion on that? Like, you need to see whether the model that has already been pre-trained, is the performance good enough for you? Then you can, use it to fine tune for your specific purpose.